Using the basic ideas of logic and how the language of circuitry is constructed and interpreted, this video will go on to describe how these principles are applied to a real-world example, the computer. What you should appreciate by the end of this video is that the flow of information and the logic of circuitry can once again be described using truth tables and the same types of gates that were described in the previous video. The only difference you should see is in the gate symbols themselves, which have been adapted to include those that are used in electronics. To begin, it's helpful to recognize first that the flow of information in electronics is looking at the flow of electricity. At the atomic level, we can describe this as a flow of electrons. This is how information essentially moves through an electronic circuit. Going back to a diagram from the first lecture video, we can describe electronic processors using the same elements, where there is a source of information, which in this case is an input of electric current, the actual processor itself, and then the final output. A common type of information processor used in electronics is known as a transistor. A picture of what an actual transistor might look like on the outside can be seen at the bottom of this slide. Notice that we can see there are three basic parts labeled E, B, and C. These stand for emitter, base, and collector respectively. The fine details of how a transistor works can be viewed in a video on YouTube at the address shown here. I highly recommend that you stop this video at this time and view it because it gives a great summary of the basic chemistry and theory for how a transistor works. You are not required to view the YouTube link and you won't be tested on any of its details. I simply recommend it because it is informative. What you need to understand about transistors in the context of circuitry and this lecture series is as follows. First, we can use a simple illustration for a transistor like the one shown here. Notice once again that we see the three pieces, the base, the collector, and the emitter. These pieces can be assigned a role in the flow of information. The base serves as where the information flows in, or the input, and the collector is the output. So what does the third piece, the emitter, do? If you watch the YouTube video, in their transistor diagram, what they called the drain is the emitter, the source is the collector, and the base is what they called the gate. Notice how when we look at this picture, if we just flip it on its side, we now have the essential pieces between the two diagrams in the same orientation. In addition, up until now, we've had a black circle included in this diagram on the left to represent where the processing takes place. Let's now remove this circle to show you the complete universal diagram for a transistor that you would find in any literature on electronics. Once again, notice how the two diagrams are designed exactly the same. What you should appreciate when looking at these pictures is that the logic for the processor is captured in this middle section where the gate or base is located. This is because this is where the electronic switch is turned on and off. The critical idea is to envision that this circle is where there will be a flow of information or not. Recall that this flow of information is in the form of an electric current. Let's now see how a transistor works in an electronic circuit. First, imagine that our transistor is one of the parts that you would find in a simple on-off light switch. Let's start with our switch off. In electronics, we assign a switch that is off with a truth value of 0, meaning that no current is flowing into the circuit. In this state, when the input value is 0, this means there isn't any current that is flowing between the collector and emitter. You may also see this referred to as the gate is open. If we then want to view the opposite case and say, let there be light, we can turn on the switch, which subsequently changes the input truth value to 1. We've now allowed a current to flow into the circuit, and we can envision the gate as being closed, meaning there is a complete connection between the base, the collector, and emitter, and this is allowing a current to flow between them. The key points from the last few slides are summarized once again here. The critical connections you should be making at this time with the previous videos in this lecture series is first, you should understand that an information processor in electronics has the same features and respective attached roles as we've seen before. And second, to recognize that the logic and decision of a transistor relies upon whether there's a flow of an electronic current or not. To see how the input truth value at the base leads to a specific output from the collector, I've added a second illustration that differs slightly from the first, but the key elements are still present. We still have an input, but now we can refer to it simply as the switch. And we also have the collector and emitter, which is sometimes also called the ground. The reason for why this piece is named this way will become evident in a few more slides. At this time, hopefully you will have noticed that the collector and output are now shown as two separate pieces. And there is a new element in this diagram called a resistor. The resistor is actually a part of the collector. It is essentially the part of the circuit that allows the transistor to process the information and make a decision in the form of the output truth value. To see what this resistor does and how it is tied into the language of an electronic circuit, we need to envision our two scenarios as before, with the switch being in either the on or the off position. In our first case, with the base or switch starting in the off position, we saw before that this gives us a truth input value of 0 and no electric current is flowing within the processor. Similarly, we can use the diagram on the right to also envision this flow of information, where the input value is still 0, meaning the switch is left in an open or off position, and we can see that the electric current is not flowing between the emitter and the output. Hopefully this illustration makes more sense to you as to why the switch is sometimes called a gate. We'll describe how to arrive at the output truth value in a few more slides. In our second case, when we flip the switch and close the gate, we can then change the truth input value to 1. At this time, you should envision that there is an electric current flowing within the processor because there is a complete closed-loop connection between the ground, the switch, and the elements that will determine the output truth value. Another useful way to envision an electric current is to think of water flowing through a pipe. The amount of water passing a given point per second is analogous to the flow of electrons, and we use the term amperage or simply amp to describe this flow rate. Hopefully what you can envision is that in order to have the water or electrons to flow from one region to the next, there needs to be what we call a potential energy difference between the two regions. We use the word potential because the energy difference could be used to do work. In our pipe diagram, we've shown here that there's a height difference which causes the water to flow from the top to the bottom. This means there is a gravitational potential energy difference that could be harnessed and used to power other things. Similarly, in electronics, the whole goal is we want to power other things, which means we must have the electrons flowing from one region to the next, and there needs to be an electrical potential difference. This potential energy is something also referred to simply as the voltage. So how do we create this potential energy difference in our transistor? In the transistor, we also see that there are different places where the current can flow. From the base, between the emitter and collector, etc. So using our water analogy, we can envision that our transistor is actually an interconnected system of pipes. If we alter our diagrams to make them look like a system that forms a closed loop, we can see that regions of high pressure and low pressure are created by the combined action of a pump, a bottom reservoir, and gravity. This is what leads to the potential difference and allows the water to flow in this example. In an electric circuit, the combined action of the switch and the ground is what creates the potential electrical difference. We call it the ground because the electric wire is actually connected to the ground as a way to dissipate or drain the electric current and maintain the potential difference. In this case, the power plant and the wires connected to your home have a higher potential energy and thus provide the input electricity that can be accessed when you flip on a switch to your electrical device. Likewise, the electric circuits in your home are also organized the same way, and you can see this with every outlet and plug, where one part of the circuit is connected to the ground and the rest is connected to the electrical grid. I've taken the time to explain how the language of a transistor is established and transmitted to begin with, because this basic knowledge is needed to be able to comprehend first why we have the collector resistor, and second, how is it the key element in the decision-making of the transistor. To begin, we can think of the resistor as being a smaller point in the water pipe like you see here, and it's the same idea with our electric current. The purpose of the resistor is to restrict or limit the current across that particular region of the loop. If we envision our water or electrons as having a particular flow rate before the resistor, this narrowing of the pipe limits their passage in this region, and fewer water molecules or electrons will move through the resistor within a given time frame. Thus, we can see that one of the roles of the resistor is to also help maintain the potential energy difference. In electronics, the resistor is usually made of a different material that is less conductive than the rest of the material, which means it takes more energy for the electrons to move through it. We can see this energy difference labeled in our picture, where there are 12 volts before the resistor and a very small value close to 0 volts after it. If we also add where the collector and output pieces would be in this diagram, we can see that they are ideally situated to access the electrical potential before and after the resistor. This is how they are involved in the decision-making logic of the transistor. To see how we arrive at a final output truth value, let's envision our simplest case, where the switch is off and there is no current flowing. At this stage, what you should be envisioning is that we've removed a source of energy because the water pump or electric switch has been put in the off position and the current is no longer flowing. But this doesn't mean that the pipes or electric wires are actually empty, right? Eventually, the water molecules in the pipe and the electrons in the wire will follow basic physical laws, meaning that the potential difference will dissipate over time across the connected parts of the system. If we look at our actual transistor, the switch being open means the electrons don't flow to the ground and they are maintained in the upper portion. If we look at the voltage between the collector and the output, what we find is that there is no potential energy difference between them, and they are approximately the same. The logic of the transistor is designed to report an output truth value of 1 in this case. In the transistor diagram, we show this output value by filling the circles like we've done here with a red color. If we look at the opposite case, where the switch is closed, this means the current can then flow between the elements, and we can see that a potential energy difference is generated due to the physical properties of the resistor and the connection to the ground, which drains the excess electrons away. When this happens, the logic of the transistor is designed to report an output truth value of 0, and you will notice the small circles at the collector and output terminals remain unfilled. At this time, hopefully you've made the link that the overall logic of a transistor seems to be designed to invert the truth input value, right? See how the one input becomes an output of 0 and vice versa? Haven't we seen this before when we described the logic of a NOT gate in the last lecture video? Hopefully you can begin to see how the principles of an electronic circuit can be connected with the gate logic you were exposed to before. In these last few slides, you will see some examples for how transistors are used in the construction of different electronic gates with a specific type of logic.